Okay, so we're going to continue where we left off in the last class. This is a quick recap where we left off. We were speaking of training a neural network. So this is how we set up the problem. You're given a training set of input-output pairs, XD, where each X is the input to the network and D is the desired output of the network. We defined a divergence between the actual output of the network, which is given by this function here, which has the parameters W, which are the parameters of the network. And so the divergence was defined between this F and the desired response of the network in response to X. We defined a loss, which was the average divergence over the entire training set. And to train the network, we minimized this loss with respect to W. This is a problem of function minimization. In order to actually perform this minimization, we need to define several things, including what are these input-output pairs, what is this function f, and what is this divergence. So we defined all of these. The function f was just a multi-layer perceptron, a directed network with inputs and outputs. So any input was processed sequentially from the input to the output, and no neuron revisited an input. The individual neurons in the network were perceptrons of this kind, which operated on affine combinations of the input. And finally, an activation function was applied to this affine combination. The activation function itself, we said, must be differentiable, and we saw different instances of activation functions. So the input and output were defined like so. The input X is typically a vector of real valued numbers. The desired output in response to X depends on the problem. If you're trying to make real valued predictions, then the desired output would be a vector of real numbers. If you are performing a classification task, then the desired output is going to be a one-hot vector representation of the label. And we saw in the last class that although it's a one-hot vector, you have two ways of viewing it. You can just think of this as a vector of numbers, or you can think of this as the ideal output a posteriori probability of the class for the training instance. So for example, if the desired output for a class was 0, 1, 0, 0, 0, then you can view this as this probability distribution function, in which case you're saying, I want the network to output the probability of class given input. And specifically, I wanted to assign a probability of 1 to the correct class and 0 to all of the remaining classes. This is the desired output. The actual output, again, this could differ, and when the network is not perfect, it will differ from the desired output. If you're trying to make real valued predictions, the actual output is going to be a vector of reals. If you're performing classification, the output is going to be a probability distribution over the labels. So we defined all these three things. We have defined F, and we've defined input-output pairs. The last thing that we were left with was the divergence function, which is where we stopped. Then we saw that for real valued outputs, a popular and a very reasonable divergence function between the actual output of the network and the desired output of the network was given by this formula here, which is half of the squared Euclidean distance between the desired output vector and the target output and the actual output vector. And this has a nice, since one of the things we want to do when we are performing backpropagation is that we want to compute the derivative of the divergence with respect to the individual parameters of the network, we need to be able to differentiate this divergence. And in this particular case, if you actually compute the derivative of the divergence is a function of many outputs. The network has many outputs. So the derivative of this divergence is going to be a vector. And the ith component of this vector is going to be the derivative of this guy with respect to yi, which is simply going to be yi minus di. You just work out the derivative. This is what it comes out to be. It's going to be the error in predicting the ith component. For classification tasks, we saw that there are two ways of dealing with the definition of the divergence. Here, if you have a binary classification task, then you just have a single output d, which is either going to be 1 or 0. Now, one way to look at it is to say this is just a number. The other way to look at it is say this is the probability of the target class given the output. If you simply look at it as a number, then the reasonable divergence is going to be half y minus d squared, and the derivative is going to be y minus d. Whereas if you think of this as a probability and that you want the network to assign a probability of 0 if the training input is not from the class, and a probability of 1 if the training input is from the class, then a much more reasonable divergence function is going to be the Kullback-Leibler divergence between these two guys, which is given by minus d log y minus 1 minus d log 1 minus y. This is where we left off in the last class. Now let's take a look at how this works. You have two possibilities. The training instance is from the target class. If the training instance is from the target class, you have d equals 1, meaning 1 minus d equals 0. So the divergence is going to be simply, this term goes away, the second term goes away. The divergence is going to be minus log y. You have the other condition where the training instance is, what happened? Where the training instance is not from the class. And if the training instance is not from the class, then that's my one note messed up. Okay. Then you're going to have d equals 0. This is the desired output. So in this case, if d equals 0, minus d log y equals 0, and minus 1 minus d log 1 minus y is simply going to be minus of log of 1 minus y. So the second term remains. These are the two conditions, right? Observe what happens. Basically, you want, if your desired output is 1, then y must be 1, log y will be 0, and so the divergence is 0. If the desired output is 1 and you output a 0, then you're infinitely wrong. Log of 0 is minus infinity. Minus of minus infinity is infinity, so you're going to get infinite divergence. So this has a very nice property. And similarly, if your desired output is 0 and then you output a 1, you're going to get 1 minus 1 is 0, so log of 0 is minus infinity. Minus of minus infinity is infinity. So when you make an error, the divergence is going to be infinity. But if the desired output is 0 and y is also 0, then 1 minus 0 is 1. The log of 1 is 0. The divergence will be 0. So this divergence has a very nice property. And furthermore, if you actually compute the divergence, when the desired output is 1, d is 1, this term as we saw goes away, you're left with just minus log y. The derivative is minus of 1 over y. When the target output is 0, then this guy goes away. You're left with log of 1 minus y, and the derivative of that with respect to y is 1 over 1 minus y. So we saw this in the last class, the last thing. If I compare the Euclidean divergence with the KL divergence, when the desired output is 0, here is what the Euclidean divergence looks like. It's the red curve. Whereas the Kullback-Leibler divergence is given by this blue curve. And you can see that the Kullback-Leibler divergence is 0 at the correct answer. The x-axis is y here. It becomes infinity at the exact wrong answer. Similarly, when the desired output is 1, then you can see that the Euclidean divergence, again, the L2 divergence does have a minimum out here, but then it's very shallow, the curve. Whereas the Kullback-Leibler divergence, it also has a 0 out here, but when the network is exactly wrong, it's predicting the exact opposite of what you want, the divergence becomes infinity. So in classification problems, the Kullback-Leibler divergence is much more reasonable than the L2 divergence. There was another thing that happened. If you look at the derivative over here, let's say the desired output is 1, then the derivative is minus 1 over y. When y takes the correct value, y is going to be 1. So the slope is actually going to be minus 1. It's not going to be 0. When you have the correct answer, the derivative of the divergence is minus 1. So also, if the desired output is 0, then y becomes, when you have the correct answer, when the network is actually outputting a 0, you find that the slope is 1. So in either case, the derivative of the divergence is not 0 at the correct answers, which is why we said what we really want to do for when you perform gradient descent is to check if the function is continuing to decrease. Simply inspecting the divergence is not going to give you a sufficiently good criterion. Now, that is for a binary problem where you have only one class. This is is this a cat or is this not a cat problem? When we had multi-class problems, then for multi-class problems, the target output is going to be a one-hot vector with many components. The actual output of the network also has many components. In this case, the Kullback-Leibler divergence is given by this formula, which is going to be the KL. Let me see if I can get rid of all of this. The KL divergence is going to be between y and d is given by minus summation. What do I have on the slide? I forget. It's going to be summation. It's going to be summation di log di minus summation di log yi. Now observe how this behaves. Your desired output is going to have this kind of a property. It's a one-hot vector. This is d. Okay? And your actual output is going to have this kind of a structure: minus y1, y2, y3, y4, y5, y6. This is y. And so consider the second term. You're taking this d and multiplying it by the log of the corresponding y. For the one-hot vector, this is the only guy that's going to give you a reasonable value. All of these other guys are z's. So only for the correct class are you going to have d value 1, and for all the incorrect classes, the d value is 0. So this second term is simply going to be minus of log of the output of the network for the correct class, and everything else becomes 0. Now this first term over here is not a function of the output of the network. We can safely ignore its properties. So when you actually take a derivative, this is all you have. You only have the negative of the log of the probability assigned to the correct class by the network. So the derivative of the divergence with respect to the output of the network is going to be 0 for all of the incorrect classes. It's going to be minus 1 over the output of the network for the correct class. Now look at what happens over here. This is you want the output of the network is always positive because you're computing probabilities. So y is always positive, right? So this guy is always telling you that the divergence is going to decrease if you increase y, because the divergence is always going to be negative with respect to y. Y is always positive. So 1 over y is always positive. So for the correct component, the derivative is negative. And we saw in the last class that when the derivative is negative, it's encouraging that value to increase. So it's always saying it's going to try to increase y. And once again, when you have the correct answer, the derivative is not zero. So in your homeworks, you've been looking at cross entropy loss rather than the Kullback-Leibler divergence. The Kullback-Leibler divergence is given by this formula. This first term is not a function of y. So you can just focus on the second term and minimize just the second term, and it should give you the same optimal value of y. And just the second term is what we will call the cross entropy loss. Now, specifically when d is 1 hot, either d is 0 or d is 1. When d is 0, when the component of d is 0, because this outer guy is 0, this term is going to become 0. When d is 1, log of 1 is 0, so this guy is going to become 0. So this entire first term is going to disappear. And so the KL divergence between d and y is going to be exactly the same as the cross entropy loss between the two. Again, the cross entropy is not a divergence. The Kullback-Leibler divergence is a divergence, but the two are the same when we use 1 hot representations. So all terms have been defined. Questions, anybody? I'm going to just flow on. So if you have any questions, ask now.
There's nothing on chat, by the way. I think you're doing a really good job.
Okay. So I'm assuming you have understood all of this. Here's what we've got. Neural networks are universal approximators. They are trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual output and the desired output for the training instances. And to train them, we have to define the network, the manner in which the inputs are represented, the manner in which the outputs are represented, and the divergence between the actual and desired outputs. So we've done this. And now we are set to actually continue with working on the problem. Here again is our problem setup. You're given a collection of training instances. You've defined a divergence between the actual output of the network and the desired output of the network for each of these training instances. Our loss is the average of the divergence over all of the training instances. This is what we're going to minimize with respect to W. And we are going to minimize this using gradient descent. We've already seen what gradient descent is in the last class. So here is the gradient descent algorithm again. Let's say I have some function L of W, which I'm minimizing with respect to W. So I initialize my W, and then at each iteration, I adjust because I'm trying to minimize L of W. And we saw in the last class that the gradient, what was the gradient? Which direction did the gradient represent? Anybody recall? What was the direction of the gradient? What did it represent? Guys?
Maximum.
Pardon me?
Direction of maximum change.
The direction of maximum change, right? So is it just the maximum change?
Maximum increase.
It's a direction of maximum increase, right? So you want to decrease the function, which means you're going to walk in exactly the opposite direction of the gradient, which is why you adjust the W against the gradient. You subtract some scaled version of the gradient and iteratively continue this process until the function L is no longer decreasing. And although this is written in vector form, if you want to sort of look at it more carefully, you're basically going over it component by component. And for each component of W, you're subtracting some scaled version of the derivative of L with respect to that component of W, the partial derivative of L with respect to that W. Again, remember the gradient was just the vector of partial derivatives. This is what we're going to use to train the neural network, except here I've just written one common vector W. In fact, in your neural network, you have many weights. Now, does anybody remember what this notation for the weight meant? Anyone? We introduced this in the last class. What was this? Someone?
Someone on the chat says kth layer.
Kth layer, what are the subscripts? Anybody?
The weight from neuron J arriving at neuron I.
It was actually neuron I in the k-1th layer, arriving at neuron J in the kth layer. So these are for the kth layer neurons, right? And so the actual gradient descent rule is going to be that for every weight, we are going to subtract a scaling factor times the derivative of this loss with respect to that specific weight, which means we must be able to compute this derivative. And this is what we need to be able to do. Now, again, the loss is the average of the divergences of the entire training set. So if I want the derivative of the loss with respect to a specific weight, that is going to be the average just by the linearity of differentiation. That is going to be the derivative, the average of the derivative of the divergences for the individual training instances with respect to that weight. Which means what we really need to compute is this guy. We need to know how to compute the derivative of the divergence for a single training instance with respect to each of the weights. If you can do that, then you can compute the derivative of the loss, which is the average of these divergences over the entire training set. And so we're going to focus on this guy. Questions, anyone? Any questions on chat, Rashmi?
So someone's asking here, T refers to the number of training examples, right?
Exactly. Okay. Now, so basic laws of calculus. We're going to spend some time talking about calculus again. This class is going to be calculus heavy. How did we, if I have a function y equals f of x, how did we define the derivative of y with respect to x? I have y equals f of x. So what was the correct way of writing the derivative? Anybody remember?
Delta y equals alpha delta x, where alpha
Delta y equals alpha x delta x, right? And now if x is a vector, then what was alpha going to be?
A row vector?
A row vector of what?
Partial derivatives.
Of partial derivatives. And what was the final formula? When I compute this operation, what was the final formula going to be in this case? Anyone? Just plug it in, right? This is going to be the partial derivative with respect to x1 times delta x1 plus the partial derivative with respect to x2 times delta x2 and so on. Anyone who doesn't remember this? This just falls out of the definition, doesn't it? Raise your hands if you remember this. I want to see how many hands are raised. Okay, 50 is good enough. All right. So because I'm going to just build on this really quickly, okay? And I fear that this class is also going to stretch, but that's okay. It's important to get this right. Now, so for any differentiable function y equals f of x, this is the definition we had. When x was scalar, I can just write the derivative as dy over dx. When x was a vector, the derivative was a row vector of partial derivatives, and this is the relationship that we got. We remember this, right? So now here is my claim. I'm going to say that if I have a function y equals, it's a function that operates on another function g. So y equals f of g of x. Does anybody remember the chain rule for computing the derivative of y with respect to x? What was it? Anyone?
dy dg dg dx.
dy over dg times, I'm assuming everything's a scalar here, dg over dx. So how can we use the basic definition of derivatives to prove this? Let me show you, right? All I have to do is I know that dy equals f prime of x, right? Or let me write this my own way. Is dy over dx, this is my derivative, times delta x. So I need to be able to plug this formula in here, and if it's valid, then I've shown that this property indeed holds. Let me write z equals g of x and y equals f of z. So now, using our definition of derivatives, what is delta z? Anyone?
dz dx times delta x.
It's the derivative g prime times delta x, right? And the delta y is f prime times delta z, correct? So let me plug this in here. It says delta y equals f prime times, and I'm going to use this formula for delta z, g prime times delta x. I can parenthesize this, and this guy is the same as this one. So we have proved that this chain rule holds. Questions? Anyone?
Nothing on chat.
Okay, fine. So now I'm going to, I'd like you guys to help me with something slightly more complex. Okay, we're going to work on this problem here. I have, let me clarify, clean this out. I have y equals f of g1 of x, g2 of x, all the way up to gm of x. So what was dy over dx? Do you remember? Anyone? This was
f prime dot g prime dot delta x.
This is going to be f prime. What is f prime?
Df by dg.
Df, but then there are many g's.
So in this case, it's df by dg1 dot dx1 dot dx. Sorry.
dg1 dot df by dx. Is that it?
Plus df by dg2 dot dg2 by dx and so on up till
dg2 over dx and so on till the end. Can we prove this? How would we prove this? How would we prove this?
I think it's the same way as you prove alpha.
Correct. I need to be able to show that delta y equals dy over dx times delta x. If I can show that this property holds, then it is correct. Now, let me just say zi equals gi of x, right? And I say y equals f of z1, z2, and so on. Now, if zi equals gi of x, then what is delta zi? Anyone? What is delta zi?
gi prime times delta x.
is gi prime times delta x. And for the lower guy, we've already shown this, right? What is delta y over here? Again, you remember this, right? It is the partial of f with respect to z1 times delta z1 plus the partial of f with respect to z2 times delta z2 and so on. Remember this? We just did it, right? And I can plug this formula here, right here. That's going to be the partial of f with respect to z1 times g1 prime times delta x plus the partial of f with respect to z2 times g2 prime times delta of x and so on, which I can just pull out the x's and I can write this in like so. Partial of f with respect to z1 times g1 prime plus partial of f with respect to z2 times g2 prime, the whole thing multiplied by delta of x. And then if you compare this term at the bottom with respect to the formula we had up here, I mean with the formula that we had up here, you're going to see that they are the same formula, right? And so this kind of follows that this property holds. We just sort of showed it. Questions? Anybody who didn't get it, raise your hands. Any questions on chat?
No.
Okay, fine. So this is the property that we're going to be using all over the place, but we are going to use it in a different way. We're going to begin drawing what I call influence diagrams. So look at this formula here. So the way I can write it is this way. I can say that I have my x and I'm using x influences z1 through zn. And each of these in turn influence y. We saw this diagram earlier in the last class as well. So how much does a small perturbation in delta x change delta y? A small perturbation in delta x is going to cause a small perturbation in each of these guys. And when you get fine enough, delta y is going to be summation I delta zi, meaning it's going to be the perturbation in y is going to be the sum of the perturbations that come through all of these lines. And the perturbation in z is simply going to be delta x times dz over dx. So that's basically how the whole thing works, which means that the derivative of y with respect to x is going to be the sum of the derivatives for every one of these functions, every one of these paths. And so if you ask me if I can draw this influence diagram, then it's easy enough for me to say that dy over dx is d1 prime plus d2 prime plus g3 prime. I just have to follow each of these chains to find out how a small perturbation in x changes y. So small perturbations in x called small perturbations in each of these z's. Each of these additively individually perturbs y. And so that's going to give me my, so the derivative of y with respect to z is going to be the sum of these partial derivatives. Questions?
Someone on the chat is asking, here we assume that the coefficient for each edge is 1, right?
The coefficients, we are only speaking of influence. There are no weights. I'm saying x influences z, z affects y. So which variable affects which variable? That's all we are drawing. I'm calling this an influence diagram, not a weighted diagram, right? I just wrote down all of the variables and said changing x changes z, changing z changes y. Did you get that? We're going to keep reusing influence diagrams, so it's kind of important to get this, okay? So now we're returning to our problem, which is how do I compute? Yeah. There's a little poll. Thank you. The answer, of course, is that it's true. Now, for those of you who could not see the poll, here it is on section 6. This was the poll. I'll flash this briefly before I continue. Anyway, so now the question is, how do you compute the derivative of the divergence with respect to the individual weights? For that, I'm going to sort of work off this tiny 2-input illustration where I have a network going left to right, and there are only 2 hidden layers. Each layer has 2 neurons. But then let's look more closely at these neurons. Each neuron actually has 2 individual operations going on. First, you compute an affine combination of the inputs, then you put it through an activation function. And so I will separate the 2 in my picture. Moreover, I'm going to actually represent each of the weights. Remember, the notation that we had for the weights was when I wrote when I wrote something like W. When I wrote Wij raised to k, then this was the k minus 1th layer. This was the kth layer. This I represents the ith neuron in the k minus 1th layer. The j represents the jth neuron in the kth layer. So this is the weight of the connection from the ith neuron in the k minus 1th layer to the jth neuron in the kth layer. The superscript represents the destination layer. So also, instead of explicitly showing a bias, I've just added an extra 1 at the bottom. I've augmented all of the layers by an extra 1 to account for the bias, so I don't need to explicitly show the bias. So here is the figure again. Let me also begin labeling the other variables, the intermediate variables. The z's are the affine values. So again, noting the if I write z, j, k, then this is the affine value at the input to the jth neuron in the kth layer. If I write y, j, k, this is in parentheses, okay? Then this is going to be, that is, how did the rest of the figure disappear? This is going to be the output of the jth neuron and the kth layer. So the subscript is the neuron index, the superscript is the layer index. This is for a single input, and x goes in, the neuron computes the network computes a y. I have a desired output d, so I can compute the divergence between d and y. The output doesn't have to be a scalar, it can be a vector, as we saw. And what we really want to compute is the derivative of this divergence with respect to the individual weights of the network. Now, remember that when we wanted to compute the derivatives, again, remember that the derivative of a function really depended on where you are at the function. The derivative could be very different at different points. So you need to know where you are in order to compute the derivative. And where you are in the case of the network is specified by all the intermediate variables in the network. So before you can compute the derivative of the divergence with respect to any parameter, you need to know the output of the network, and you also need to know all of these intermediate values because they specify where you are in the input space, where you're computing the derivative. So as a first step, all of these highlighted values and the network output must be computed. And for that, before you begin computing derivatives, you will start off with the input and first pass it through the network in what we call the forward pass, and compute all of these intermediate variables. And so we'll just go through this in a quick animation here. Again, this is showing, I've sort of expanded the net a bit. I'm showing the affine values at the input of each activation and the output of each activation. Everything is being shown in this network. These ones account for the bias. Now, the input, I can think of this as the output of the 0th layer, just for uniformity of representation. So when I say y superscript 0, that just represents the input. Now, consider just this first guy. What is the affine value at the input of this first neuron? That is going to be a weighted sum of all of these inputs. Specifically, you're summing over all of these guys, and what you're summing is the value here times the weight of this edge. So it's going to be the ith value y times the weight from the ith value here to the first neuron. This is because we're only considering the first neuron. You sum this over all of these guys, and that's going to give you the affine combination out here. And you can just generalize this to all of these neurons in the first layer. So the affine combination coming in to any neuron, to the jth neuron, is going to be the sum over all of the values in the previous layer. So here, because we are looking at the first layer, this is for you'll be summing over all of the outputs of the 0th layer, which are the inputs here, and you're summing the y value times the weight, wij. So the ith value in the previous layer is being multiplied by the weight from the ith neuron in the previous layer to the jth neuron in the current layer to compute the affine combination at the jth neuron. This is the formula that gives you the affine combination for every one of these neurons. Once you've computed these affine values, you can put all of these affine values through their corresponding activations, and you're going to get the outputs for all of the neurons in the first layer. Then you can use these outputs and repeat the same computation as you had out here to compute the affine values at the neurons, for the neurons in the second layer. And now, of course, you're going to be using the weights for the second layer neurons. And once you've computed these affine values, you can pass them all through the activation functions, and you're going to be you will obtain the outputs of the neurons in the second layer. You can just continue this, then use these to compute the affine values for the third layer and pass those through the activations. Keep computing this all the way till you get the outputs for the neurons in the final layer, and these are going to be the outputs of the network. Now, I sort of flashed through the whole process, but does anybody have any questions over here about every single equation? The equations are so simple that they shouldn't raise much doubt, but let's pause for a minute for questions. Questions, anyone?
So there was one question about influence diagram. Our student was asking, can I think of an influence diagram as a weighted diagram where all the weights are 1?
So we are strictly speaking of influences. If you think of this as a weighted diagram, you will get into trouble when you're trying to look for more generic settings. For example, in a couple of classes, we will try to draw the influence diagram for batch normalization. And you will see how applying weights sort of can cause issues. Just think of it, any weighting is part of the function. Look over here. So if I go back to my influence diagram, if there's a weight associated with z, that weight is within the function g. This is only showing the influence, nothing else. I'm saying z influences y. Does that make it clear? I assume so. Okay, so now here is the forward computation. Again, I'm going to set the 0th layer values as my input. Then I step through the layers. Within each layer, I go through all of the neurons. For each neuron, I first compute the affine combination, and then I pass the affine combination through the activation function to get the output of the activation. Simple enough. So I have some pseudocode explaining the whole process. I'm not going to explain the pseudocode itself. There are pseudocode littered all over the slides, but here's the basic idea. You set the input, then you go through the layers. Within each layer, you go through all the neurons for the layer, compute the affine value for the neuron, and then finally compute the output of the activation for the neuron. The final output of the network is going to be the output of the neurons in the final layer of the net. So we've gone through the neural network left to right, and in the process, we have computed every single intermediate value in the network. All of these z's and all of these y's for every neuron in every layer. Now, we have the network output, we have the desired output. We can use these to compute the divergence between the actual output of the network and the desired output of the network. Now, here is where we are going to begin computing the derivative. First, we're going to assume that this divergence is a differentiable function. I emphasized multiple times that you need the divergence to be a differentiable function. If the divergence is differentiable, then you can compute the derivative of the divergence with respect to each of the outputs of the network. Once you compute the derivatives with respect to the divergence with respect to each of the outputs of the network, we can then take a step back and use this to compute the derivative with respect to the affine values going into the neurons in the final layer. And then you can take another step back and use these derivatives to compute the derivatives for the weights of the final layer neurons. The derivatives of the divergence with respect to the weights of the final layer neurons. And then you can take a step back and compute the derivatives with respect to the outputs of the penultimate layer neurons. Take another step back and then compute a derivative with respect to the affine inputs to the penultimate layer neurons. And then another step back, the derivatives with respect to the weights, and keep going backwards in this manner till you eventually compute the derivatives with respect to the weights of the first hidden layer. And interestingly enough, you can continue this all the way back and compute the derivatives even with respect to the inputs. Again, remember what the derivative is really giving you is the information about how much a small perturbation of the value is going to change the divergence. So you can use this process to even compute the derivatives for the inputs, which will tell you how much a small perturbation of this guy is going to change the divergence. That's going to be used in some fun problems down the line. So because we are actually going in from the end to the beginning, when you compute the derivatives, you're pushing the derivatives backwards through the network. So we will call this back propagation or backward gradient computation. So let's actually see the math really quickly. First, very first thing, we're going to assume that the derivative of the divergence with respect to the outputs of the network can be computed. So and this is of course also the derivative of the divergence with respect to the outputs of the final layer neurons. So this is available. This is how the derivative is defined. Now let's take a step back. I have the derivative of the, we've already seen some of the divergence formulae. So we know this is computable. But there are other divergences which we'll see in later classes which could be more complex. So computing this term can be complex. But for now, let's assume that it's computable. If you can compute it, then we can take a step back. Let's consider this first neuron. For this first neuron, I have the derivative with respect to, I already have d of the divergence. What I want is to compute the derivative with respect to the affine value for the first neuron. But this, using the chain rule, I can say is the derivative of the divergence with respect to the output of the neuron times the derivative of the output of the neuron with respect to the affine value, right? This is just a straight up chain rule. And of course, this guy, the derivative with respect to the output we assumed is available. We've also assumed that this activation function is differentiable. So this derivative, the derivative of y with respect to z, is simply the derivative of the activation computed at the current value of the affine, the current value of this affine term. And of course, this current value of the affine term was already derived in the forward pass. And so I can just plug this f prime out here. And this tells me how to compute the derivative of the divergence with respect to this affine term here. And just generalizing this, I can use the same formula to compute the derivative of the divergence with respect to the affine inputs of all of the final layer neurons. So we've taken the first step backwards. Questions, anyone? Any questions here?
Nothing on chat.
Okay. So now, what about the derivative with respect to the weight? So let's consider the first neuron, just this guy, this edge. So this is the connection from the first neuron in the n-1th layer to the first neuron in the nth layer. So if I want the derivative of the divergence with respect to d1, w11, using the chain rule, I can write that as the derivative of the divergence with respect to the z, which is z1, times the derivative of the z1 with respect to the weight. Correct? And the derivative of the divergence with respect to z, we just computed as we were going backwards. So the only thing that remains is now to compute the derivative of z1 with respect to w11. Again, now this term is what remains to be computed. But then remember what this affine combination was. This affine combination here was this y value times this weight plus a bunch of other terms which came from these other guys. So z1 was w11 times y1. So this is y1 from the n-1th layer plus a bunch of other terms. So if I take the derivative of z1 with respect to w11, all I'm going to be left with is y1, which is the y value at the end of the connection. So I can plug that in. So, and this y value has already been computed in the forward pass. So I can plug that into the formula right here. And so this term is going to give me the derivative of the divergence with respect to the weight of this connection. Just generalizing. The derivative of the divergence with respect to any weight is going to be the input, the derivative of the divergence with respect to the weight for any connection is going to be the input of the connection times the derivative of the divergence with respect to the affine value at the output of the connection. So if I take this guy, the derivative of the divergence with respect to this weight is going to be this term times the derivative of the divergence with respect to this guy. That's basically what this is showing. You can use it to compute the derivatives for all of these weights. And now I can take a step back. I can compute now the derivative of the divergence with respect to the outputs of all of these neurons. And the derivatives for the outputs of these neurons, again, this is a little more complex. Now consider this first neuron over here. It's useful to think again in terms of influence diagrams. I have a bunch of neurons in the n-1th layer. I have a bunch of neurons in the nth layer. Now the output of this neuron influences every the outputs of every one of these guys, right? So Y influences the affine combinations at each one of these guys. What happened? My one node disappeared. These are all the things you don't account for. Okay, Y, close it. This Y influences the affine combinations here for every one of these neurons. So, and these affine combinations go ahead and influence the outputs of these neurons, and all of them affect the divergence. So if I were to draw the influence diagram, the influence diagram is going to say that I have a bunch of Z's, Z1 through Zn, whatever, Zd, right? And Y influences every one of these Z's, and each of these Z's influence the divergence. So if I want the derivative of the divergence with respect to Y, I must sort of sum over, this is going to be the sum over all of these Z's of the derivative of the divergence with respect to Z times the derivative of Z with respect to Y, simply because of the nature of the influence. So that's what this figure is showing. And the derivative of the divergence with respect to Z has already been computed. And from this formula, which we saw earlier, the derivative of Z with respect to Y is simply going to be the derivative of the Z of any Z with respect to Y is simply going to be the weight of the connection between the two, which I can write here, right? So generalizing, the derivative of the divergence with respect to any Y is going to be a sum over all of these Z's of the derivative of the divergence with respect to these Z terms times the weight of the connection between the Y and the Z. So so now we managed to compute the derivatives all the way to the output of the neurons in the n-1th layer. Anybody have any confusions about this equation? It's very straightforward. Maybe explaining it is a little tedious, but if you have questions. Anyone? Rashmi, anything on? No, none on chat? Okay. So now that I've obtained the derivatives for Y, I can take a step back and I can just multiply, I can compute the derivatives with respect to these Z terms, and using the same chain rule, that's going to be the derivative with respect to these Y's times the derivative of these activations. And then I can go back, use the same formula to compute the derivatives of the divergences with respect to all of these weights. Take a step back, compute the derivatives of the divergences with respect to the outputs of the neurons in the previous layer, and then the previous affine values, I can work my way back all the way till I compute the derivatives for the weights to the first hidden layer, or even the inputs. So this is the entire backward computation. In the first step, we obtain the derivatives of the divergence with respect to the outputs of the network, and we assume that this term can be computed. Then we take a step back and compute the derivatives of the divergence with respect to the affine inputs to these neurons. Then you go backwards through the layers, and within each layer you go through all of the neurons, and then first you compute the derivative of the divergence with respect to the Y using the formula we just saw, which is going to be just a weighted sum of the derivatives of the divergence with respect to these Z's. Then you can take another step back and compute the derivatives for the affine inputs to the neurons. And also in the process, you can compute the derivatives of the for the weights which connect these Y's to these Z's using the formula over here. Again, the derivative for any weight is going to be the Y value at the input to the connection times the derivative for the Z value at the output of the connection. So this is the entire backward propagation code. It's very, very simple, the algorithm. I have pseudocode for it. I'm going to skip it. But then I assume that this whole thing was clear. Was it clear?
So we have a question about this does not take into account activation functions. Is that correct?
Here is the activate. This is, you have this guy here is the derivative of your activation function. Once you compute the derivative for y, as you take a step back, the next thing you do is to compute the derivative for the affine input for the neuron. That's obtained from this formula here, which is the derivative for y times the derivative of the activation function. Did that answer your question?
Yes, it does.
Okay. So it sort of works your way backwards. Go through the slides. That's probably the most tedious thing you're going to see through the course, okay? So in this entire process, I've made some assumptions. I've assumed that the computation of the output for one neuron does not directly affect the computation for other neurons in the same or previous layers. We've assumed that the neurons are of the kind where you first compute an affine combination of inputs and then apply an activation. And we've assumed that the activations are differentiable. Now, all of these assumptions can be invalidated. So I'm going to just look at some of these topics. Not everything is going to be explained, but they're on the slides, so please look at the slides. This will appear in the quiz. Now, first thing, what I will call vector activations. Now, what do I mean by vector activations? In all of the, I'm going to distinguish between two kinds of activation functions. In this, so consider a single set of neurons over here. In this entire layer, if I just modify this one Z, the only Y that changes is going to be the corresponding Y. So this is a scalar activation where there's a one-to-one correspondence, strict one-to-one relationship between the affine input and the activated output. But then here's a different one where a collection of Z's go in and a collection of Y's come out. Here, if I change this one Z, not only is the single Y going to change, every one of these Y's is going to change. So this is what I will call a scalar activation. Modifying a Z only changes the corresponding Y. In a vector activation, I have a vector of Z's going in. Modifying any Z potentially changes all the Y's. So here I can write this in terms of a bunch of scalar functions. Each Y is a scalar function of a scalar Z. I cannot write this kind of activation in this manner. Here I have a vector Y, which is a function of a vector Z. So this, of course, changes the manner in which you compute the derivatives. Let's take a look at the influence diagrams again. Here, a single Z only influences a single Y. Here, each Z influences every Y. And in turn, every Y is influenced by every Z. So in the scalar case, if I want to compute the derivative of the divergence with respect to Z, I first only I can just use the chain rule and say that is the derivative of the divergence with respect to Y times the derivative of Y with respect to Z. A simple chain rule will do the job. In the vector case, don't look at the formula. How is this going to change? So if I have something of this kind, how will this formula change? If I want to compute the derivative of the divergence with respect to, say, Z1, what is the formula here going to be? Anyone?
I think it will become the summation of partial derivative on partial Y.
Yeah, it's going to be the derivative of divergence with respect to Y times what?
times partial y partial z.
That is going to be I.
Y, yeah.
Exactly, correct? So this is, so here you actually have to begin worrying about the influences of all of these guys on the Z. Now we've seen one instance of such a vector activation function. This is the softmax activation. Remember how we computed the softmax? We exponentiated all of the Z's, but then we normalized them to such that the outputs sum to 1. So here, now, so that meant that if I increase the Z, the corresponding Y increases, but to compensate for it, the other Y's decrease. So you can see that each Z influences every Y. And all of these Y's in turn eventually influence the divergence. So if I want to compute the derivative of the divergence with respect to the Z, I have to sum over all of these Y's of the derivative of the divergence with respect to these Y's times the derivative of Y with respect to Z. Now, what is this derivative? This guy, this first term, we've already assumed that that these derivatives, as you're back propagating, coming in from the end of the network to the backwards, these have already been computed. These guys, the derivatives for these guys have been computed. So the only term that remains is the derivative of Y with respect to Z. And exactly what is that? Let's actually sort of derive it for the softmax function. This is taking some time. I have yi equals e raised to zi by summation j e raised to zj. And I can write this as e raised to zi divided by e raised to zi plus summation j not equal to I e raised to zj, right? So when I take the derivative of yi with respect to zi, that is going to be here, that here is the derivative of for this guy with respect to the corresponding z. That is simply going to be, using your standard distributed rule, the derivative of e raised to zi over zi times 1 over summation j e raised to zj plus e raised to zi times the derivative with respect to zi of 1 over summation. This is sliding over. Let me see if I have space. Summation j e raised to zj, right? So this, of course, this first term, of course, is just going to be this derivative. This is just e raised to zi times 1 over summation j e raised to zj. The second term plus e raised to zi remains. Then you have 1 over summation j e raised to zj squared times, this is minus 1, right? Times, and then the derivative of this term itself with respect to zi, which is going to be e raised to zi. So if you, and this, of course, is just yi. And here I can write this as e raised to zi over summation e raised to zj times e raised to zi over summation j e raised to zj, which is yi minus yi squared. So the for the horizontal connection, you're just going to say get the derivative of the divergence with respect to z is of the derivative of y with respect to z is y times 1 minus yi, right? But then if you look at this term, how does changing z change this second term? If you go back to your derivatives here, this first over here, if in that case, this is going to be the derivative with respect to zj. So this will become 0 because this is e raised to zi with respect to e raised to zj. So this first term is going to disappear. You're just going to be left with minus y squared. you're just going to be left with minus yi times minus yj. I suggest that you actually go through this arithmetic. I'm not going to do it because we run out of time. But then in any case, here is the point. We actually get a derivative which is going to be different for each of the y's. Every one of these y's is going to be influenced by z. And then when you compute the derivative of the divergence with respect to z, you're going to be summing over all of these y's. The derivative of the divergence with respect to y times the derivative of y with respect to z. And the derivative of each y with respect to z is different for the straight connection and for these cross connections. So the point being is actually you have to worry about the entire set of outputs and can't just think of these as just a simple relationship. Now here's another case. This is let's look at the array loop, right? We've assumed that our activation functions are differentiable. So each neuron had a z, you had a function f, and you got a y. And we assume that the function f is differentiable. But the ReLU has this property. It looks like so till here, and then like so over here. So what is the derivative of this guy? What will the derivative of the ReLU look like? Anyone? What is this derivative going to look like?
Heaviside function.
It's going to be 0 until here, right? And on this, and what about at this value? At this location, what is the derivative?
Undefined.
Undefined, right? So if you were computing a derivative, what value would you choose? You need to put some number in there for your backprop. Which one would you choose?
If it's based off homework 0, 1.
It turns out you can choose any value between these two guys. Any value at all. So again, go back and think of what the derivative means. The derivative is telling you the direction of maximum increase, right? But then in the more generally, when you can't compute a derivative, you would look for a derivative where the function does increase. In this case, it turns out that if I consider this slope, that slope captures this line, right? If I look at this slope, that slope captures this line at this point. And then there are all of these lines with different slopes, all of which lie entirely under the function. I can take any of these guys and use their slope in lieu of dy over dz, and it will work. So these things are what are called subgradients. You can't actually compute the derivative, but you can find a line or a hyperplane which touches the curve at this point and lies strictly below the curve. And if you take the slope of that guy, or more generally the normal to that plane, that can also be employed in the gradient descent rule. So for the ReLU, you can use the slopes of any of these guys. You can use any slope between 0 and 1 for f prime of z, and it will work. Now, so in the homework, we just use the largest value because you had to pick, that's all. Now, there's another function. Did that make sense to you guys? Why would you not choose something that's less than 0 over here? Anyone want to take a guess at why you would choose, why you would not use something that was less than 0?
The line would not be below the function.
So you're going to get something of this kind. That's going to be the slope of the line. So you're actually asking the network to shift the function in a decreasing direction, right? I mean, think of a leaky ReLU. For a leaky ReLU too, you have the same problem, right? So if you have a leaky ReLU, then the value that you would use is not going to be between 0 and 1. The leaky ReLU has a slope which is something else, maybe of this kind. And so for a leaky ReLU, you're going to use a derivative that's in this range. If you use something outside that range, then the leaky ReLU would have a function of this kind. And if you use a derivative that's lower than this guy, that's the direction in which you're trying to push the function. So you'll be pushing the function in the wrong direction. So you always want to, if you want to make sure that you're pointing in a direction of increase, you want to be using a slope between those two boundaries. Now, same thing with maxes. Here's another activation function, which is the max activation function. Let's so in the case of the ReLU, how that works is probably best seen if you actually plug it into a multidimensional function. But for a max, it's much simpler. Suppose I have a y equals max of a, b, c, right? And a is the largest value. Then which value would I choose? Anyone? What's the output going to be?
A.
So y equals a. Now remember, the derivative says how much is the y going to increase if I perturb these values by a little bit. So what will the derivative with respect to c be in this case? Anyone want to take a guess?
0.
Yeah, because c is not the largest value. So perturbing it by a tiny amount is not going to change y. Y is going to stay with a, correct? So this is going to be 0. What about b?
Also 0.
And what about a?
Why?
Because y is a, right? So the derivative is going to be 1 only for the largest value, and it's going to be 0 for everything else. It's the equivalent of the subgradient again. The point is, when you're picking a max of a bunch of values, this is something that we will use, then only perturbing the largest value is going to change y. You can perturb the other guys and it's not going to change y. And so the derivative is going to be 1 for the largest guy and 0 for the rest. So here is the overall approach for training. For each data instance, we're given a bunch of training instances. For each data instance, we're going to do a forward pass. First, Rashmi, can you pull up the poll for the max function?
Sorry, I don't think I have access. Can Angshan do it?
I can take care of it.
Yes.
Here's a poll. Guys, there's a poll.
Can everyone see it?
Yeah.
It says select all
select
except
all.
y, but I can only select one of the answers.
Is that right? Okay, there's something wrong over here. I must have set it up wrong. And end the poll here. So only about 90 people are actually watching the class at this point. So dy over dz3 is 1. dy over dz2 and dy over dz1 are both going to be 0, right? So this is correct, and this is correct, and this is 1. This is right. Anyway, I have sort of undershot what I intended to present here by about 20 minutes. So I'm going to record a second lecture of 20 minutes and put it out later today. But here is the overall training approach. You have a forward pass. For each data instance, you're going to pass the data instance through the network and store all the intermediate outputs. Then you sweep backwards through the network and iteratively compute all derivatives, the derivatives of the divergence with respect to the weights of all of the weights in the network. So the overall derivative of the loss is going to be the average of all of these divergences, and you'd use backprop to compute all of these derivatives, and finally use the gradient descent rule to compute the update the parameters. And so again, there's one final poll before I let you go, which is this one here. There's one final poll, guys.
Professor, can you show your OneNote of the poll? Because the recording cannot show the poll.
Oh, I'll show them both as soon as this is done.
Okay.
This one's slightly better. I'm getting more than 100 responses. Okay, I'm going to stop it right here, right? Obviously, backpropagation is only used to compute the derivatives of the divergence with respect to model parameters for individual training instances. It's not the process of training the network, and it isn't used to update model parameters. It's used to it's just used to compute the derivatives of the divergences. So this was the second poll for the max, and this was the last poll. Now I'll stop right here, and I'm going to post, I can take some questions. I'm going to post an extra lecture of 20 minutes later in the day for you guys to watch. Questions, anyone?
None on chat.
Okay. Thank you. You can stop the recording.